Welcome to the Explainer. Today, we're going to break down one of the hottest and honestly most misunderstood concepts in AI right now, mixture of experts. This is the secret sauce that lets these massive models get bigger and bigger without just grinding to a complete halt.
So let's just dive right into the core problem, right? The biggest challenge in AI today is this constant trade-off. We know for a fact that making models bigger, feeding them more data, giving them more parameters, makes them smarter. But if you just scale them up the old-fashioned way, they become incredibly slow and just ridiculously expensive to run. So the billion-dollar question is, how do you get all the benefits of that massive scale without the crippling cost?
Well, you might think the solution is some brand new sci-fi breakthrough, but actually, the answer is way more interesting. It's a really clever idea that dates all the way back to 1991. Just dust it off and give it a powerful new life in the age of deep learning.
Okay, so to really understand how this works today, we've got to jump in the time machine and head back to the 90s. We're talking about a time when models had just a few hundred parameters, and a huge challenge was just trying to get a computer to tell the difference between vowel sounds.
The core concept is, it's brilliantly simple. Just think of it like a big, complex project at work. You've got your gating network. That's the project manager. Its job is to look at any task that comes in. And then you've got a team of experts who are basically your specialist consultants. The manager's whole job is to figure out which consultant is the right one for that specific task.
Now, here's the real kicker about how they did it back then. It was called a dense model for a reason. The manager didn't just pick one specialist. Nope. It asked every single one of them for their opinion on every single task. The final answer was a combination of everything they all said. So the goal here wasn't efficiency, not at all. It was all about getting the most accurate answer possible by committee.
All right, now let's hit fast forward a few decades. The world of deep learning is exploding. Models are getting massive, and the main goal has completely flipped on its head. Now, efficiency is the name of the game.
And this is the modern revolution, the big aha moment. It's all about one word: sparsity. Instead of asking every single expert for their input, the manager now just picks the best one or two for the job, the top K, and tells the rest to sit this one out. This one tiny change is what lets models have a gigantic number of parameters, but only actually use a small fraction of them for any given problem. And that makes them incredibly efficient.
And the results of this shift? They were absolutely staggering. A typical big model at the time, something like BERT, had around 340 million parameters. The first major sparse MOE model, 137 times billion. That is over 400 times larger. And yet, because it was only using a tiny piece of itself at any one time, it was still super fast.
What's really crucial here, and kind of funny, is that even the researchers who built it were a little baffled. The math suggested that just turning these experts on and off like light switches should cause some serious problems. But in classic machine learning fashion, they basically said, well, it looks scary in theory, but in practice, it just works.
Okay, so now we get the concept, right? We see where it came from. So let's look at how this powerful little component actually gets plugged into the huge language models that we all use today.
So, a standard transformer layer has two main jobs. First, you've got the self-attention block. The best way to think about this is like a team meeting where all the words in a sentence look at each other to figure out the context. Then you've got the feed-forward network, or FFN. This is like everyone going back to their own desk to do their own individual thinking and processing.
The MOE upgrade is so simple, but it's profound. It takes that one single, one-size-fits-all thinking step, and it replaces it with a whole team of specialized thinkers. That's our mixture of experts.
And this is where it gets really powerful. The model isn't just picking one set of experts for a whole paragraph. Oh no, it is making a brand new choice for every single word or token. So for a sentence like, on the riverbank, the router might send the word river to an expert that's good with nature concepts. And then for the next word, bank, it can send it to that same expert, correctly guiding the meaning away from finance. It's pretty incredible.
And if you look around today, all the big open source models are just riffing on this basic recipe. You've got Mixtral, which uses 8 experts and picks the best 2 for every token. Then you have DeepSeek, which uses even more experts, but they're smaller, and they add this cool idea of a shared expert that everyone has to consult, kind of like some mandatory corporate training on general knowledge. And it looks like Meta's latest models are heading down a pretty similar path.
Okay, so this brings us to one of the biggest points of confusion, something you see argued about online all the time. Does our little specialist consultant analogy actually hold up? Do these experts really learn to specialize in different things? The simple answer is yes. They absolutely have to specialize.
And we can be pretty confident about this, not because we can peek inside the model's brain, but just by thinking through the alternatives, which, frankly, just don't make any logical sense at all.
I mean, let's just think it through. There are really only two other ways this could work. One, all the experts are clones of each other. Well, if that's true, why bother having more than one? It's pointless. We know that doesn't work. Two, the assignments are totally random. For that to be effective, the manager would need a ridiculously huge address book just to remember where it sent every possible word in the universe. Both of those are absurd. So specialization isn't just a nice idea, it's the only logical outcome for this architecture to work.
So where does all the confusion come from then? Well, it's because we humans, we like simple, clean, readable labels. In the early days, with smaller models, you actually could see clear specializations, like one expert would handle adjectives, another would handle punctuation. But in today's gigantic models, the patterns they're learning are just way too complex and abstract for us to slap a label on like sports or science. The specialization is definitely real, it's just not always understandable to us.
And this leaves us with a pretty fascinating final thought, doesn't it? The engine that's driving some of the most advanced AI on the planet today isn't some brand new invention. It's a clever revival of an idea from 30 years ago. It really makes you wonder, what other brilliant ideas from the past are just sitting out there on a shelf, waiting for the right moment and the right technology to come along and change the world all over again?